On the last problem in the incline planes worksheet that I've given you guys, we give you guys a scenario about something being pushed up an incline or given an initial velocity. It's allowed to slide up the incline and then it's allowed to slide back down, and we ask you to draw a force body diagram, but we also ask you to compare the acceleration on the way up and on the way down. So let me angle this surface upwards, and let's just kind of analyze the motion here. We'll see if I can get this going. I'm just going to send it up the incline, and what you're going to notice is that it slows down pretty quickly. And then that might have been a little bit hard to compare the velocity, so let me decrease the incline ever so slightly. Send it up again, and it stopped. Let's go a little bit higher. There we go. Alright, so make it so that you can see it. Let's send it up and let it come back down. So pretty quick to stop, but takes a lot longer to get back down. So what you're hopefully seeing is that the rate of deceleration here far exceeds the rate of acceleration that it goes back down the incline with. So let's try it one more time. Not bad. Slows down pretty fast, but it takes a longer time to get back down. So clearly the rate of deceleration and the rate of acceleration differ. And what we have to think about is why that's happening here. So if I draw my object here, initially what I have it doing is I have it going up the incline with a velocity in that direction. So if we're thinking about forces here, essentially we've got gravity. We've got the normal force. And then we need some kinetic friction to oppose the motion. So I'm going to have it along the surface in that direction there. And then on the way back down, let's take a look at what's happening here. You know, it's got a velocity direction that's that way. So this can be tricky because what ends up happening is that we have the same forces in play, same types of forces. You have normal force, you've got gravity, but what's going to happen is, because your motion in reverse direction, your friction, your kinetic friction, needs to oppose the direction as well. So we learned that the kinetic friction value should be the same because the surface isn't changing, but what it has done is it has completely reversed direction. And this will be a lot more clear when we get into components as to what is really happening here. Gravity can be broken down into the x component and the y component. And let's leave the normal force alone. Let's leave the friction alone. And what I want you to see here is that when we look at the x direction here, these two forces, the kinetic friction and the x component of gravity, they're working with each other, hand in hand. Now let's look at the case of when it's traveling downwards, down the incline. There's your gravity vectors. No, these are the same. Your normal force is also unaffected. But now your kinetic friction is this way. And, you know, what we saw in the examples, the demonstration that I just did to you, was that clearly I think that had to be greater than that because you watched it go back down. So the fact that they're working hand in hand together on this case right here, I would expect sigma F to be directed in this direction because these are the only two forces that are left over after these two cancel out. And they're working together, so these would add up. These are working against each other. So even though sigma F is still in the same exact direction, what I find is that this one is greater than this one. So I would expect the acceleration on the way up, which is deceleration, to be greater than the acceleration that is on the way down, which is acceleration, speeding up on the way down. So hopefully that becomes a lot more clear once you've seen that happen.